Good afternoon, everyone. Thank you all for joining us today in our weekly webinar series. Today our featured topic is fiber optic system design. My name is Jessica Petrohoy and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is the leading provider of fiber optic products, training, and rental equipment. We're pleased to present this topic to you today. With us today to talk about fiber optic system design is Jack Ioneer. Jack is one of our senior instructors and a field technician with over 25 years in managing and testing networks. Remember that our webinar series are recorded and available to you online at fiberoptic.com/webinar. And when Jack is finished, we'll take questions from the GoToWebinar question box at the bottom of the screen for a question and answer session. So thank you again for joining us today. And at this time, I turn the presentation over to Jack.
Good afternoon. Welcome to the webinar session, System Design Part 2. Hopefully you all were on Part 1, so if you do have any questions, you can type them in, referring backwards, and I can explain where we are. As we proceed, a little bit more about myself. I am a BICSI RCDD and technician and a former BICSI certified instructor also. As we continue with this Part 2 of fiber optic system design, one of the first things that we want to discuss is what Part 1 recap, what happened last month. And before you see the topics where we talked about planning the network, some operational requirements that you had to consider, the types of fiber available, the physical environmental requirements, inside plant routings, and even outside plant routings. As we continue this month, we're going to be discussing choosing individual components. We're going to take a brief look at a power budget, talk about testing and documentation, and some preliminary cost estimates. Not actual pricing, but to give you an idea of the value of different things in comparison. And also some practical considerations, and then we'll wrap up with a question period at the end. Well, this is a basic overview of some of our more sophisticated classes, both in fiber optic design for, say, fiber to the desktop or premises and outside plant design. So you're going to get a little taste of what's in both of these. But as we continue with fiber optic design Part 2, we're going to pick up on choosing basic components a little bit. And it's going to be a basic overview here. We look at transmission equipment and, of course, the devices that we consider as transmitters. And we'll also discuss receivers as we go. So in the multi-mode world, we have historically had the LED, or light-emitting diode, as the light source. And the LED was considered to be an overfilled launch condition, which means the light was a very broad spectrum width and tend to flood a core of a multi-mode. Of course, the LED is for short distance, low power, relatively low speeds, but at the point of, for a long time, up to 622 megabits was pretty quick, but they were actually very, very low cost, very cheap. And as we approach gigabit speeds, and certainly today we're well beyond gigabit speeds, there was a need for a new multi-mode fiber, and this would be in the premises. So they developed the VIC cell, which had a restricted mode launch condition. It took very little power and was capable of gigahertz modulation. So often today, to mate up with a cable, you're going to hear the words OM3 and OM4, laser optimized fiber, which should have been covered in the first section. Now, as far as that, it was very much a question that we needed more power in the premise, or distance and speed. And an option would be go to single mode. And at that point in time, that would greatly impact the cost of wiring commercial buildings and campuses and such. So the VIC cell was a limited capacity laser, not as powerful or as low spectral width as a real single mode laser. So the VCSEL was born, and obviously the OM3s and 4 were two grades of fiber optic or tweaks on multi-mode options that would get us to the gigabit and beyond the gigabit as far as light sources. So there was a need to carry the high speed even to the desk without the need necessarily to take single mode throughout or even to the desk in that case. Now if you look over on the, let's call it the outside plant or long distance side or single mode, although single mode is very, very common in campus environments of, say, customer-owned outside plant. That generally is the Fabre Pro laser. It has a fairly wide spectral width of about 4 nanometers. Now, I'll give you an idea, if a central wavelength, right on the tip is 1550 nanometers, that means the actual beam width is totally about 4 nanometers wide, and that's considered wide. So it was capable up to about 10 gigabits modulation and was a digital transmission only. It was not particularly temperature sensitive. If you continue on the options, the DFB or distributed feedback laser was much more expensive, was a narrow spectral width, typically less than 1 nanometer in width. So its data modulations are beyond 10 gigabits. And they were used for both analog and digital, and when dense wave division multiplexing applications. They are temperature sensitive and do require a conditioned environment. Now, when you think about the 1 nanometer width, if you're doing any type of multiplexing, in this case we mentioned dense wave, that just means I can get signals at different wavelengths much, much closer together without stepping on the adjacent wavelength with other distribution issues. Now, if I continue with the receiver themselves, and these are technically, I guess, some of the classifications, but there is a positive intrinsic negative diode, often referred to as a PNP. It's used in multi-mode and signal mode. It's low power requirements, inexpensive, limited sensitivity, and was an analog and digital system. In fact, the only one predominantly used in the analog. Now, the picture you see here is kind of a sensitivity by wavelength and by the receiver's doping or the glass. So you can see in a multi-mode wavelengths, it's typically had been a silicon type of dope. And then the next generation that operated up around 1310 and 5050 used a germanium-based doping material for the lens itself. And then as we went even faster, or went beyond the 1550 wavelength, up past or 21625, you notice that the response rates on the little graph shows you that the germanium receiver really fell off in sensitivity as you approached even longer wavelengths beyond 1600 nanometers. In that case, the indium gallium arsenide was invented or put out or deployed so that we could go longer through the wavelength spectrum without giving up a lot of sensitivity or responsivity in the old 1550. In other words, it's going to be much more money, but it can do both. The Avalanche photodiodes are typically single mode only, very high cost and complex. Now, if you can think, it produces a gain or it amplifies a photocurrent received by up to 10 or 50 times. So it's not an analog system device. It's very sensitive to ambient temperatures. Under the amplifiers or transmitters, the semiconductor optical amplifier you'll see designated as OSA. So it's a laser. It's one of the original 1310 and 1550s, direct amplification of up to 12 decibels, and can be used bidirectional. The EDFA that you hear about is an yttrium-doped fiber amplifier, and it actually uses a pump laser that operates at 980 nanometers, optical amplification up to 35 dB and operates in the C-band of the spectrum. And it's typically what's used with DWDM. And if you can see the chart on your screen, it's a doped length of fiber. It's inside the amplifier, and it's very much like kind of a turbocharger. It will boost the signals as they go out. A little bit more now, but I think that's all we really need to cover today. And then there are passive optical devices used in wave division multiplexing, optical switches, and some of the add-drop multiplexers. Now, cable designs would have been covered to some extent, and we're looking at the basically indoor, which historically are each individual fiber tight buffered, or let's say encapsulated with a 900 micron tight buffer plastic coating, much like an individual wire with insulation if it were electrical. They fall into three categories you see here. Distribution is a bunch of 900, and I'll put my arrow on it here, 900 tight buffered fibers just packed together in one design, often uses the building riser cable. Hence the word distribution, the cable that is used to distribute, say, the fiber throughout the building in the case of a commercial building. Breakout cable, which is shown next to it, I'll move my little cursor over here, and if you look closely at the picture, it is many simplex, standalone fiber optic patch cords, if you want to use that bundled together, and hence the term breakout. I can take, I believe the maximum is up to about 72 fibers conveniently in one cable. Let's say from, if you have a incoming ports on one side of a room and have to get cable over to the switches on the other side, let's say it's 100 feet. And you wouldn't run individual, say, 72 fibers over. You'd run this particular breakout cable in between the points. So it kind of gives you a nice coherent bundle. And when you break out, since generally they would serve as a long patch cord, then each one would in essence be a standalone 3mm patch cord, for instance. Hence the term breakout. And then cordage, not shown here, would be the individual ones. Now, as you move outdoors, they tend to be loose tube buffered or loose buffer tubes, often gel filled. And the first picture, if you can see, put the arrow on here, my cursor, is what we call a stranded design, meaning that they are helically wrapped around a central strength member, the tubes, each tube containing typically 12 250 coated fibers. That's pretty much the standard design for outside plant cable. The unitube design shown next to it is a central core, and in smaller counts has become very popular as all fibers are contained in a single inner tube. Unitube is the generic description for that. Now the last thing here is a word about armored, and you can see the unitube cable on this particular drawing here does have the conventional corrugated armoring for outside plant cables. So that would be typical of telephony copper cables also. So the industry is very familiar with armored. Now armored with a single armor, as you can see under the jacket, is pretty much a standard outside plant. But depending on applications, you can get double jackets, doubled armor configuration depending on the environmental deployment that it's intended to. And that's a basic rundown on cable designs. If any of you are into industrial plants, oil and gas industry, you'll also find that many of them will deploy outside tight buffered outside designs, typically for harsh environments. So if you see that, as you can imagine, it's like, it actually looks like a little bit of a breakout cable. but they are helically stranded and totally protected and often used in what you would call harsh environments. Extremely expensive for conventional pole line construction, but very common in industrial, petrochem, anything you can think of, harsh environment type of stuff. Now, what terminations do you use, or what plugs do you use, and who makes that decision? And I sometimes joke that often we think we make decisions, or you say the plant engineer makes a decision, but sometimes I say that's not quite accurate. Often the questions that you need to decide are, what do we have existing, and are we or should we continue to use that system? Many of the familiar connectors are on the way on obsolescence because of the high-speed data that we're running in today's networks, where you get beyond 100 gig and even more. So it's driven by the transmission equipment, I guess, is the point here, not so much by the guy that's going to build the plant. And it can be called out in a standard, but the standards will allow several different types of connectors to be chosen. Ultimately, what I like to say, it's usually the electronics box people that really make this determine. Is Cisco shipping the latest, greatest multiplexing equipment with the little half-size LCs or Larry Charlie connectors, then that's pretty much going to determine what connectors you're going to use throughout your physical plant. Now, having said that, here are your options. The SC, or SAM, TOM, or straight tip, was the bayonet quick disconnect. It's pretty much no longer on the building wiring standards, and was mostly multi-mode. It's pretty much gone, although there are thousands and thousands being sold. Now, where the standards start to come in is that there is a standardization. And the most common one is the picture I have up here in the green, which depicts a square type, or a SC, Sam Charlie, or subscriber connector, common throughout the 90s and even to today. It would be the standard TIA 568 official approved connector. Now, because of the transmission rates and back reflections, the picture I have up there being green depicts a negative 70 dB back reflection of what we call an angle polish connector. So we've gone, because of these high transmit speeds, to a physical standard like the SC, but then go further down to the ferrule tip and polish it somewhere. To give you an idea, an old standard connector, SC, was probably around 28 to 30 negative dB back reflectance. You just heard me say the APC is up around negative 70. Very, very little back reflectance. There's also commonly used, which would be blue in color, and you may see them in some of the FiOS types of boxes also, would be the blue SC, which would indicate basically a ultra polish, which would fall in the negative 50 range. So there are your termination options. Now, the LC is really the dominant connector today. And so that's the half size, or instead of being 2.5 millimeter, it's 1/2 of that, or 0.125. So the story on that is basically density. We always want to get more and more into our fiber optic designs. What used to be a 48-port box, I want it to be a 96-port box without removing it by replacing it. Now, shown in the picture is not an LC. You're going to see a multi-fiber push-on, or an MPO. And these little MPOs are kind of the footprint of like a copper RJ jack, and can carry anywhere from 2, certainly past 12 or more fibers in the nose of the MPO shown there. Now, the next slide will continue with the termination options. Now, we do make a mention for the FC. The FC was the older screw-on. It kind of looked like an ST, which was the bayonet disconnect, but was a screw-on and was a central office type of connector. Don't see it much anymore, except you will still see it on many of your testing equipment. the test sleeve that connects to a light source, say a light source, is often, because you calibrate it, screwed into the light source, giving an excellent connector. Now, I've already been talking about the MPO, multi-fiber push-on, and mostly used in data centers and are really, really for high density. Here you see a good example of a rack with a couple of types coming out with tails. So the ones on the left are duplex LCs, or the small form factor half-size connector. And each individual connector is a fiber. And then right next to it you see another option, say for backbone runs, would be these multi-fiber push-ons, where, as I said, each connector ferrule could probably hold 2 or certainly 12 and even 24, say 2 rows of 12. So you can see where it's gone. We want the extremely high data transmission rates, but real estate in a building or any place that we have is extremely expensive, so we want to get as much as we can. And these are the solutions used pretty much today on all fronts. Now, you heard me talk about the power budgets. Well, not yet. You heard me talk about the back reflections that we needed to lower from what was normally, say, a -30 to as low as almost lossless back reflections, a negative, say, 70 even. And that brings us to the topic of a loss budget. With these high performance systems of 100 gigabits and above even, that then the loss of power and back reflection is part of the loss of the power. But the light coming back towards a transmitter through losses occurred through connectors has to be trimmed down. And that's the whole idea, the low loss back reflection of the, let's say, ultra and the angle polish connector. I'm not going to go into great detail, but suffice it to say that every little bit of light that is lost through the transmission, through our physical plant, our cables, our connectors, our splices, at 100 gigabits or even more, has to be pretty much accounted for. And too much backfeed or back reflection heading back to a transmitter can affect, say, the quality of a picture for a cable TV company, or could even begin to damage and affect the outbound signal or affect a very expensive laser amplifier. So as we pull out the stops, we've got to get more and more accuracy and minimum in loss. Now here's a simple design. Fortunately, for us in the physical plant world, it's pretty simple calculation, or what I say, easy math. The fiber itself, or the light traveling through the glass, is really the only component of our physical plant that is wavelength sensitive and is based on your design. Currently, if I were transmitting at 1310, just one of the options that I have, the loss could be as much as a half a dB per kilometer of distance. But the same fiber at 1550 would be more like 0.22. In fact, at 1310, most fibers today are really running around 0.35 dB per kilometer. So the calculation of your loss budget has to be done at operational wavelengths. We need to know what the loss is and how it fits into the range between, or the sensitivity between an amplifier and receiver through our cable plant to determine how well the system will work for our cable plant. But as I said, since the fiber is wavelength sensitive, we would calculate that, because what would work at 1310 might barely work at 1550 and not work at all at 1625, where losses are lower but become extremely more sensitive. So here's the little math formula if we build a physical plant. It simply says that I'm going to have a length of cable that loses, in this case at 1550, let's zero in on that, 0.22 per kilometer of distance. So if I had 1 kilometer, I would expect light normally traveling through that length of fiber to lose 0.22. Now the components themselves are pretty much, they are not wavelength specific. So the second item that we have here is what's the splice losses. Now normally this is a budget, and for inside plant people, if you're doing pigtail splicing, the EIA recognizes 0.3. Well, 0.3 mechanical splice or fusion splice, although we all know that really wouldn't be acceptable fusion splice. But the budgets for outside plant average out of the EIA, or excuse me, the IEEE would be that would represent a budget of a 0.1 max. Even that in most environments is not an acceptable for a fusion splice. Since we should get fusion splices in the 0.01 to 0.03, most of your clients or most of your designs are not going to be designed in the 0.1, but 0.1 would be a budget number, but you should get much less out of that. So it's just a simple matter that if each fusion splice is to lose 0.1 and I have 10, then I'm going to lose 1 dB through that. Now mechanical splices, you heard me say, are typically 0.3. So if I had 10 of those, it'd be 3.0. We'll do easy math in our heads here. Now the connector pairs are something else. The EIA, TIA mated connector pairs would be a maximum of 0.75 dB. Now you could say, well, that's the standards. Are standards really good? And you might say, no, what would I really expect on a high-performance system today? And so 0.75 is usable as a budget to run your calculations. Most connector pairs today, the SC, Sam Charlie, the 2.5 connector mated, should probably give me somewhere on connected pairs 0.3 or 4. While the little small form factor LC, or Larry Charlie, should consistently be down below like 0.1 or 0.2. So you can see today's tweaks of the newer style generation of connectors produce much less losses because of the polishes also than their predecessors have. And then the last thing to think about is the safety margin. Commonly it could be 3 dB. In essence, all we're doing is adding the sum of the parts, and we're going to get a number. So we can very easily, as cable designers or outside plant, easily calculate what our physical plant will eat up. Now that means that I know that number is sitting at my desk. So the average is a very old and simple concept that you see allowed here. Well, what's allowed? The transmitter has a power level or average power level. An example we use in a class, and we have quite a detailed calculation chart for you that if you've taken one of your classes you probably would have gotten. If you like a copy, just email us at etraining@fiberoptic.com and I'll be glad to send you the whole form that we use. But in simplicity, it's all about the transmit power, or in the old days I'd say the gain of an amplifier minus the sensitivity receiver, both of them measured in dBm, power, will give you a number. So if I have a negative 30 dBm amplifier, and that just means that's its power output. If my receiver sensitivity, which means let's put a number of negative 40 on that any signal less than negative 40, the receiver will not pick up, kind of a signal to noise ratio, or the receiver drops out, no signal. So if I had minus 30 and a minus 40, that gives me, drop the M, because I'm going to talk about loss now, the difference between transmitter and receiver there would be 10. I hope everybody can picture that in your head. That simply says that if my physical cable plant eats up more than 10 dB, it doesn't work. You're going to have to go out and tweak something. So the link margin, as we were talking about the sum of all the parts, is the allowed link loss is the fiber loss, but that's wavelength sensitive, so we just have to run two numbers, minus the splice loss. So I could take that 10, subtract 0.22 for fiber, subtract 1 for splice loss, and 7.5 for 10 connector pairs, and safety margin of 3, and any other thing I would have in there, because if I had splitters like on a FiOS system, they would be part of the calculation for the budget. Like I said, we can give you a much more detailed form. Just give us a call or send us an email, and we'll be glad to provide it for you. And that is the total link margin. So you see, although this can get very technical and complicated, it's based on a very, very simple formula. Power. As power goes out over distance and hits connectors and runs through the glass over time, it loses power. If it loses so much, and this is an old like copper signal to noise ratio, there is no signal for the receiver to see, and your system literally does not work. But it could have different problems associated with it if you're too close, and that's the idea of the safety margin, to allow for physical things, even defects that maybe the installer might be too tight a bends, for instance. But you can easily calculate what we call the optical power budget. Now, you heard me rattle off some splice losses. Well, they are based off of standards. And the most notable one was the TIA 568 commercial building standard, where a splice loss is 0.3. Now, typically, they don't use fusion splices, although it's becoming more common in campus networks. But it's based off the standards and does not differentiate between a fusion or a mechanical. Other losses are simply determined by best practices of the company. I've had people in class who may be subcontracted to Cox Communications, for instance, and they have a spec that Cox will accept no fusion splice greater than 0.03. But then they could go work for another municipality somewhere, and they may be using 0.05. Now that is the company's best practices that you're working for. Now it may be the guy that will accept extremely low loss only. It might just tell you that perhaps he's got an older legacy system and may be a concern on how many additional splices are added and what their values are. That's about all I could do for that. Now, it also says the real splice loss doesn't come out of your splicer. The splicer will only tell you what an estimate is. So you could have a 0-0 on your splice machine, and the only way you're going to know the actual loss is by shooting it with an OTDR, which will tell you the exact loss of the splice. So your perfect 0-0 for the fusion splicer might in fact be a 0.01 or 0.002. Although the splicers are pretty good, it's not. It has to be validated by the OTDR results. Now here you see just a simple point. The blue line represents a power level, and as light travels through glass over distance, so it starts at a high power and continues downward to the right as it travels through glass. Here it shows you when it enters, say, a mechanical splice interface and comes out the other side, the difference between power in minus power out, and you probably just heard that a slide before, is in fact the loss of that splice. So if I was at 10 dB hitting that splice and I come out at 9.99, I've lost like 0.1 or 0.01. Pretty simple. Now the connectors are based off of standards, but could also be best company, and the only validation of your standard loss would be your OTDR test results. Now, you also heard me say that today's connectors are well below published EIA or TIA commercial building and the IEEE outside plant. Connector losses are the same in both arenas, and based off a standard, you would expect less based on the polish of the ferrule tip that you have. So that'll give you an idea of why you might pick a connector. And it is about your cable plan and your loss budgets, which I said were easily calculated. And then it's a matter of, amplifier. Now, the thing is what happens if I get a number that's really close to, like, I ate it all up at 1550, then what are your options? Well, physical plant options sometimes are not very flexible. In other words, we build it, we know what it is, we're probably not going to rip it out. Often you can look back to the amplifier or the switch package. Was the design of the switch itself enough power to make the distance that your physical cable plant is? So very often problems can be fixed by a different type of switch. To say that I could go out and get perfect connectors and perfect splices only and fix it, you really have to consider you're probably not going to do that. Or how long, depending on the environment, will that perfect connector matings stay perfect? So usually there's a couple things that you can look at as you do your cable design. So it's not based on real complicated stuff. And here's our fiber loss, the dB per kilometer specified wavelength. Well, what's going to tell me that? Well, the instrument that's going to tell me that is the optical time domain reflectometer result. This is why you should shoot a reel before you install it, and with an OTDR. There is, if the cable is out of specification for some reason, then you can determine that right away. If you pull the cable and wherever you got your cable from, it's out of spec, say 0.2 dB per kilometer, that's what you paid for. If it's higher than that, then it should go back to the manufacturer. It's not within specifications. If you've already installed it, you're very likely to be forced to live with it, and you really don't want to be in that position. And if you are a contractor, you don't want to put yourself in that position, because the end user may, in fact, demand compensation or demand it be pulled out and pulled back in. So that's a good point here at this about the OTDR testing results. And of course, when constructed, you build it. Now here we go, other anticipated losses. Well, losses to wave division multiplexers, attenuators, splitters, couplers. And we typically think of splitters, especially in the FiO systems, where one single mode fiber can feed up to 32, say, users. So that's mirrors. So if I split a fiber, just got a two-way splitter, one fiber would split into two, and it'd be 50% loss is what, like I said, I'll keep easy math. So if you're doing a fiber to the home type of thing, then you would have splitters or any other devices. I do just want to mention attenuators. It is possible to have a transmitter and receiver too close together, where a high-powered transmitter at a short distance from the receiver can, in fact, saturate the receiver. And you can physically add attenuators to the system of various dB to cut back the power if that's the problem you have. So we would have losses, although attenuators would tend to either be existing that you'd have to calculate for, or if you've anticipated them, that would be part of your budget also. Now, safety margins as far as restoration splices or span length changes due to restoration. If you had to cut out 100 feet of cable at a pole accident, but you put in 200, well, then you just added to the span length. And if your operational budget was marginal, well, you may have added actual loss to it. So you need the safety margin to include a few extra splices and the span length changes due to restoration. You know, how many slack coils do you have within the system? The aging margin is that temperature fluctuations on equipment effects. Some of the high-powered equipment you may notice out in the field, you know, boxes tied to poles with air conditioners on them, okay? And source of aging and degradation. You know, over time, and if exposed to moisture, the cable can darken and become brittle. So if any of you have ever spliced in a brand new piece of cable, you know, replacing a section that was 30 years old and had much difficulty getting it spliced together due to, say, breakage on the, you know, embedded fiber, the original fiber, that does come into play and needs to be calculated for, at least budgeted for, some sort of safety margin. Now here, we've kind of covered the dynamic range of the receiver. The input power to the receiver must fall within the range of the component. Well, what did I just say a little while ago? The output of the receiver minus the sensitivity, the output of the transmitter minus the sensitivity of the receiver. And that's the amount of loss that can occur between the two units before the receiver drops out. So it has to fall within that range. And the only thing between us and the receiver is our physical cable plant. And as I just said a slide or two ago, if you're too close together, you could have too much power. But you'd use your budget or an optical loss test set, and you can determine how much you need to cut back that power to add the system safety to within your acceptable margins that you've done on the calculation. Now, when it comes to the actual testing, especially single mode, you've heard me talk about already the optical time domain reflectometer. But we also, importantly, and if you're governed by TIA, it requires what they call Tier 1 testing with a power meter and light source, or often just an optical power meter or optical loss test set. Many of these can be combined with OTDRs depending on what you've bought, but we'll talk briefly about them. Now, why the OLTS, or the power meter and light source? Because it measures actual loss of your link. It can't see into your segment. It can't tell you anything between the light entering at point A and exiting at point B. It'll give you the overall loss. But the fact that it measures true power, it's the most accurate for total link loss testing. Now, if you compare that to what we think of the much more expensive OTDR, and certainly our best troubleshooting and testing tool, is because this can see into your cable plant. It can and will draw you a picture and can calculate the loss occurrence at each connector and in each splice. So the key word here is it's a calculation of loss based on all backscatter and reflections, because that's what it's tracking. The back reflections after the laser launch, and it will draw you the graph. So a straight line of cable with nothing in it would start high on the left at a certain power rating and diminish on a slope to the right until it finally exits the glass or runs out of power. So we're going to talk a little bit about that today. Now, what's the types of tests? Pre and post. Well, things I do before, things I do after. You notice I was specifically to tell you the things you do pre should be is to test all reels that come in while it's on a reel. Yes, that could mean stripping down 144 fibers on one end and hooking it to an OTDR to determine that you've got what you paid for, or there isn't a particular problem before you pull. Typically, we think of what we call final acceptance. So if you think of things under, there are things you do when you install or during cable pulls and installation. And there are some low-level machines that, say, installer-level personnel can use to make sure that everything is going according to specifications as you go. And then the final acceptance, you're going to send a technician out, one of your higher paid employees, and they're going to final acceptance test and document for record, for payday if you're a subcontractor. And you don't want that person having to shoot each fiber and fix something that should have been taken care of on the cable pool. In the final acceptance, you want to gather the information to produce your records to give to your client, and in essence, that could prevent your bill. We're also going to talk about OLTs, documentation, a little bit about troubleshooting here. So what tests? And I've kind of implied about the infrastructure. And when do you test? Well, we mentioned pre-installation. Boy, that's the real. On the reel. Post, you test it to verify the value of fusion splices in construction. The final, let's call that the big documentation day. Your client's going to want to know a complete fiber characterization, loss per kilometer of distance through the fiber, total distance loss testing, and details of each splice and connector pairing. Now keep in mind the spikes of a back reflection on a mated connector pair on an OTDR will give you the number for it. So if the back reflection, the height of the spike, is in essence, and I'll pick one out, negative 30 dBm. Well, that's a typical PC or flat connector from the old days. And if I am buying much more expensive ultras and I'm not getting negative 50, then either the connector's wrong, somebody's going to go out and probably clean it, but maybe change it out, or maybe substituted connectors on the install that shouldn't be there. And it's going to be a real big deal. And that's the final. And then the last bullet here says third-party maintenance testing. Periodic testing of a cable plant is important. Whether you're a third-party provider means periodically you go out and you shoot the circuits. And it's like taking an MRI at a hospital. You know, you go to a doctor and he says, I don't know what's wrong with you. Here, go take this MRI. Well, they're taking a base shot. That's your final acceptance. Here where you are. I need a baseline. You could come back 3 years later. The doctor 6 months later gets your MRI back and he goes, hey, what is it, doc? What ails me? He goes, you should have been here sooner. But anyway, so the third-party maintenance can show you deterioration in your system long before it takes you down. So you can actually see a system deteriorating. And that could be very much, if you're in an extremely dirty environment, or it would be worse than in an ultra-clean environment. So you test, the last point here is that's your permanent record. That's the baseline. And any troubleshooting done in the future, I can take new shots, compare it to the documentation, and you can get a physical picture. On most of the software, you can overlay the original right over top, or overlay the new shot, and you can actually see when, where, what has deteriorated since the last time. So that's why it's important, troubleshooting and emergency restorations. Now in the first section, I guess we went a little bit in depth into the dispersion issues associated with high power, long distance outside plant cable. Well, this says that I can test for this thing. Do most installers need to test for all of these dispersions? Most installation contractors will test for the basic OTDR, tracing the circuit, characterization, losses, loss per kilometer distance, total losses. Now for troubleshooting, for actual dispersions that occur over long distances, you can, and this is where I sometimes joke, I had a client years ago that bought a $40,000 OTDR. And he took a class but wanted me to show him how to use it. And he pulls out this $40,000 thing, and I'm sitting on a campus site. He's about 1 mile long and a half-mile wide. And I said, where are you shooting with this thing? You know, the West Coast or something. And what it was they had money, so the local sales guy thought he needed this. Now what that does is that today's platform-based OTDR probably starts at around $10,000 to $12,000. But you would not buy the modules, and you can see these are plug-in modules, bus slots. So I could buy one for PMD if that's what I test for. But a lot of these are big testing companies that you may call out to do this sort of test for you. So very expensive equipment. So I can get a PMD module. I can get a chromatic dispersion module. I can get the optical spectrum analyzer. Now that's the one that will show me all the wavelengths lined up from 12-something to 16-something if you're, multiplexing, which most people are today. I can get protocol testing devices so that my OTDR could hook up to a SONET network and talk to it an actual SONET rate and check the bit error rates based on SONET or Ethernet or ATM, whatever the network protocol you have. Well, that's basically how you can take a $10,000 or $12,000 tester or cable tester, which is what most people need, and turn it into a $40,000 piece of equipment. But if you don't need that, then you don't need to buy it. And of course, self-contained hand-on handheld units today are much, much below that $10,000 or $12,000 and can easily get one specific for your needs, certainly between $6,000 and $8,000 even today. So the equipment's come a long way. Now, when do I do a loss budget? Well, when you start, when you do the design, and you put the loss budget for worst case scenarios. And the component losses per standards are what's necessary. So we'll use 0.75 for the connector matings or 0.1 for fusion splices, even though you're probably going to do much, much better than that. But it's good for a budget. And it just says you may need attenuators to bring power down to within the receiver's range. Now the optical loss testing gives me total LAN or link loss, including all connector, splices, fiber, and any other components in. But it only gives me A to B, as I said before. It doesn't peek into it. Testing should always be done at 2 wavelengths at least, the 1310 and the 1550, which have always been the 2 standard telephony windows. And then those test results compare to what your loss budgets. And it could determine if you need an attenuator or you need some other corrections to the system, very simply. So as we said, the OTDR gives you a picture, draws you a picture of the fiber span, and can show locations and losses thousands of kilometers apart. And they should be dual wavelength. But if your OTDR has the capability to do, say, 1625, the other window, then you should do it from the start. Now, even if you're not operating in that range, but you will have a characterization record, and you can see with your documentation where potential problems might occur in your physical plant should you upgrade to other wavelengths or other types of multiplexing systems or systems. Here we talked about dispersion, Seth. I pretty much covered that there. Now, we did go in on the first about dispersion, compensating fiber, and the outside plant fibers are usually ITU specifications, which are G series, 652 predominantly. Now, so you have this dispersion compensating fiber. And what it is, it's a high negative dispersion to correct for chromatic dispersion. Now, if the spreading of the light waves could cause chromatic, basic chromatic dispersion issue over distances, the the spectrum gets wider and wider and wider. And if one crosses the other or steps on an adjacent signal, that in theory it'll step on a signal close by, or information carried on one could pass an adjacent fiber not experiencing it. And that's what they meant by dispersion. Now, not shown here, and I should have gotten a picture for it. Very often that's a passive device. It's not an actual, I'm not going to rip out 10,000 meters of cable and replace it with dispersion compensating. It's actually a tuned coil of fiber, often in a box that you could hang on a pole at a specific point, which will bring the specifications back into line. Now, the non-zero dispersion shifted comes with a slightly positive or negative dispersion, and that's really for the long haul. If you can think of it, when they opened up the 1550 window and they discovered it didn't work as well as it should, that they had the fiber was really designed at 1310, so it's a tweak on the fiber when they went. And then there are regeneration sites, which means, what is regeneration? Well, it's not a passive. Obviously, it can correct for both attenuation and dispersion by converting the light back to electronics and then retiming, reshape. So it's much like a repeater, but a regeneration will correct those types of things. Now, I threw this in just to give you an idea. If you took on, when we had non-dispersion shifting fibers, I said it was really had pretty good tight characteristics, but it was designed for the 1350 window. But as it went further towards 1550, it climbed steadily higher. So we needed to bring that dispersion issues down. And that was done by the non-zero dispersion shifted fiber. Again, it's a tweak of the fiber because most everything now is operating, say, within that 1550 range. Think of it as like the second generation of the original fibers that were out, meaning non-dispersion. I hope that chart helps a little bit just to get your hands around it. Today, non-zero dispersion shifted fiber is probably the most common fiber out there today. Then preliminary cost estimates, transmitter receiver, this is bigger than that comparison for you guys. The higher the bandwidth, the higher the equipment cost. Kind of makes sense. The longer the wavelength, the higher the equipment cost. And then the more common transmission scheme, like multiplexing, whether it's coarse wave or dense wave, it's many into one, the higher the equipment cost. So it's kind of, it's bigger than a breadbasket type of thing. Other equipment costs are rack costs, panels versus rack, outside plant closures or fiber distribution panels or hubs, and cable management on the pole. Your installation costs with, installation crews or your own crew. We recently participated in a municipality that ran its own electric. So their crews were totally capable of installing a communications network for a local municipality around here. Worked very well. So that all comes into your cost. Testing costs, with certifying, testing standards. You can pretty much go off the EIA, TIA, but or have your own. Contract testing out or perform in-house. Many contractors doing installations will often rent out and hire someone to do the final documentation. The guy that's going to be there for 3 days doing 3,000 fibers, rather than commit their own in-house personnel to it. And then there's always a question, do you purchase equipment or rent it? Occasionally rental is an excellent opportunity. And under what timeline to do the testing. As far as rental units, there's actually a couple reasons to rent. One, you only need it for a week or two. Two, you may decide to buy one because you're going to be in the testing business, and you really have to weigh that against rent a few till you get one that you like. It's kind of like, and then buy. Don't just call the local salesperson, although they'll be helpful. Then finally, as we come in here, the number of fibers, how many spares, 10%, double, the more the better. future-proofing, decide when you're going to need an upgrade, design for 25 rather than 5. And again, it's going to be on how tight your specs are on the construction. Some even suggest 75 year. And identify products, start with a spec list, test method. Here it says talk to at least 4 vendors, component manufacturers. Now, if you're talking about equipment, testers and expensive equipment for testing, like I said, rental affords you to get your hands on different manufacturers' products. Do talk with the reps, resolve conflicting facts, and know the costs impact your decision. It's like purchasing anything. You got to really balance out your needs versus the needs of the job. In other words, don't buy the 40,000 OTDR if you're not going to do PMD testing. Well, that's all I have. I don't know if any of you have any questions here. I do appreciate your time, and I don't see any questions on the board, so I'm going to go ahead and draw this to an end, and thank you very much for spending this hour with me. You all have a good day now.